Hello everyone, today we're going to be taking a look at exponentiation for arbitrary precision integers. Now, if you don't know what an arbitrary precision integer is, you should go watch my first video on that, or if you just want to recap. So, we're also going to be covering the topic of time complexity. We're going to be discussing the time complexity of certain algorithms. So if you don't know what that means, please go watch my video on that. Now, we're also going to be using some algebra. So we want to implement an algorithm for exponentiation. Now, what is exponentiation? Exponentiation is where we have some number, the base or radix, exponentiated by another number, the exponent, and this is the same as saying the base multiplied by itself the amount of times specified by the exponent, so a times a times a times a all the way up to b times. So for example, if we have 4 to the power of 3, exponentiation of 4 by 3, then this is the same as 4 times 4 times 4. 4 multiplied by itself 3 times. And this is equal to 64. So in exponentiation, we know that a to the power of 1 is a. It's just multiplied by itself one time, and a to the power of 0 is 1, and multiplying something by itself 0 times doesn't seem to make sense, but effectively when you multiply something by 1, it's the same as not doing anything, because it just gives the same number. So multiplying something by itself 0 times is defined as 1. Now, knowing this, we can already think of an implementation of exponentiation for arbitrary precision arithmetic. So let's just start by defining it. So we know that it will involve multiplication, and I've done some videos on arbitrary precision multiplication. If you want to check them out, they'll appear on the screen now. But it's not important what algorithm we use in particular. We can just say that we have some multiplication algorithm where we have, I'll use different letters, C times D. And this is some algorithm that we'll be using. It doesn't matter what algorithm it is. Now, let's use pseudocode to define our exponentiation algorithm. So we have a function, exponentiate, and we are exponentiating a to the power of b. So we need somewhere to store our answer, so let's just set that to 1. And if we're doing multiplication of a by itself b times, we can use a iteration for this. So let's say repeat b times answer equals answer times a, and this is where we're using the multiplication algorithm that we've said we're going to use before, and we don't care what it is. So we end the iteration there, and we return our answer. Now, this is an exponentiation algorithm. This is correct, and the reason that this works is, well, let's just try. So let's put in exponentiate 2 to the power of 3. or let's use the example we did before, 4 to the power of 3. So first we'll start here, set answer to 1, so our answer is initially set to 1. Then repeat b times, and this is just 3 because our second argument, our exponent, is 3. So on the first iteration we will do answer equals answer times a. So answer equals 1 times the base a, which is 4. So 1 times 4, and that's just equal to 4. Now we're on the second iteration, and that means again we do answer equals answer times a, which is 4 times 4, and that gives us 16. So now we're on the third iteration, the last iteration, and then we have to do again answer equals answer times a, 16 times 4, and that gives us 64 as our answer. And we just return this, 64. So 4 to the power of 3 equals 64. Now this isn't a proof, but it should be clear that, you know, we're repeating the amount of times as specified by the exponent, and we're in that iteration we are multiplying some past multiplication of a by itself, and that fits with the definition of exponentiation. So we will get the correct answer for any exponentiation we put in there. Now this is a working algorithm, it's correct, but there is an issue with this algorithm. This algorithm is extremely slow. So this is a slow algorithm. And now, why is this a slow algorithm? To analyze why this exponentiation algorithm, just repeatedly multiplying, is a slow algorithm, we have to look at the time complexity of the algorithm. So we will look at the asymptotic time complexity in the worst case. The first thing to look at is we have a iteration, we have repeat. We repeat b amount of times some stuff, and this is a multiplication, but we're repeating something b times. So in time complexity, we'll look at the amount of steps that something takes to execute, and if we're repeating something by b times, then the amount of steps is multiplied by b. So we can say we have b times something steps, and we'll write that in later. Now, what are we doing in each iteration? And what we're doing, as I said, is multiplication. And now, like I said initially at the start of this, we are using some multiplication algorithm, but we don't care what algorithm it is. So we can say that this has some time complexity, we don't know, it doesn't really matter, but this has a time complexity, let's say m of n, where n is the amount of digits in the number. And because we're looking at the worst case, in the worst case the two numbers will have the same amount of digits, so just m of n. And that's all we're doing in this iteration, so the amount of steps this would take is b times m of n. Now, we want this in terms of n, in terms of the amount of digits in these numbers, so n equals digits. And we want time complexity in terms of digits because that's what we operate on. And that's, you know, as the digits increase, the amount of time it takes to execute something generally increases. So we want a time complexity in terms of n, in terms of digits. So how many digits are in b, in a number? So in an arbitrary precision integer system, the integer, every integer will have some base. So we have a base for the arbitrary precision integer, and let's call that k. So our number has a base of k. So our number also has some amount of digits, and that's n. So let's say our number has 4 digits, and those digits, let's just call them w, x, y, and z. So these are the digits of our number. Now, the value of our number, which is b, will be equal to w times k to the power of 3 plus x k squared plus y k to the 1 plus z times k to the 0, which is just 1. And that's just how positional number systems work. And if we have 4 digits, that's what we get for every single number. But we want to look at the worst possible case. And in the worst possible case, what will the values of these digits be? So in the worst possible case, we will have the biggest number for the amount of digits we have. So for 4 digits in, let's say, a base 10 system, the biggest number possible is 9,999 is the biggest number possible with 4 digits. So if we look at this general case, b, we can say that every single digit of this number is going to be the biggest digit in our positional number system. So the biggest digit is going to be equal to the base minus 1. And like this in base 10, it's 10 minus 1, which equals 9. So we can call this k minus 1. So we'll have b in the absolute worst case is k minus 1 times k cubed plus k minus 1 k squared plus k minus 1 k minus 1 k plus k minus 1. And this is equal to also k to the power of 4 minus 1. And that's much like in base 10. If we have 10 to the 4 minus 1, that's 10,000 minus 1, which is 9,999, the biggest possible 4-digit number. And as we can see, this is a 4-digit number, and we have the power equal to 4. So this trend does continue to any amount of digits we have. So we will have in the worst possible case, b equals k to the power of n minus 1. Now we can go put this into our expression here for the amount of steps this algorithm will take. K to the power of n minus 1 times m of n. However, in asymptotic notation, we only look at the fastest growing factors of an expression, and here in this expression we have a exponential factor and we have a constant factor, just minus 1 and k to the n. And which factor is going to increase faster as n increases? Well, of course it's k to the power of n, because a constant is constant, it's always the same, it doesn't grow, so that's always going to be the same. So we can ignore the minus 1 and say that the real asymptotic time complexity of this algorithm is on the order of k to the power of n times m of n. So as we can see, this is an extremely slow algorithm. And why is that? It has an exponential factor. the exponential factor, if we look at how the amount of steps in an algorithm increases over time, if we make a graph of n, the amount of digits as that increases, and the amount of steps, if we have a time complexity of, say, just on, that's linear, so that'll increase at a linear rate. If we have on squared, it'll increase more like this. But if we have exponential, it will increase much, much faster, at a much higher rate. So OK to the n, that will increase just, it's exponential increase. It's an exponential increase, so it's just going to be much, much, much faster growing than these other algorithms. And because the amount of steps grows faster as the number of digits increases, that means that the algorithm gets even slower as the amount of digits increases. So this is just a very slow algorithm. Now, can we do better than this algorithm? And the thing is, we can do better. Now, how do we do that? Let's have a look. So one way that we can make our algorithm faster is through a method called exponentiation by squaring. Now, you'll see why it's called that in a bit, but spoiler alert, it uses squaring as a main feature. So if we have something like a to the power of b, the way that the algorithm is derived, we can say that if b is even, then we know that b is equal to some 2 times k, and this is a different k from before. K is some constant, some integer that is multiplied by 2, which is true for all even numbers. So we can say that a to the power of b is equal to a to the power of 2k. And now we can use the rules of logarithms to work out that a to the power of 2k is the same as a squared times k, and this is where the exponentiation by squaring comes in. And the reason we use squaring is because a number squared is simply the number multiplied by itself. So we only use one multiplication here. And now, if we do this to the power of k and we use the previous algorithm, the slow algorithm, we will see that we are using one multiplication here. And how many multiplications are we using here? We are doing this number to the power of k, exponentiating it by k. So we're repeating k times the multiplication. So this is k, and what is k? Since b is 2k, k is just b over 2. So the amount of multiplications we do in this algorithm is b over 2. Now that is an improvement of almost 2 times from the previous b multiplications, and that's very good, but we can do better. And the way that we can do better is, first of all, let's look at if it's not even, if b is odd. So we can do a similar kind of improvement, optimization, if b is odd. So if b is odd, we notice that b is equal to 2k plus 1, where k is an integer, and that's true for all odd numbers. So we can prove that a to the power of b is equal to a to the power of 2k plus 1. Now, this will become, if we apply some exponentiation rules, a to the power of 2k times a. Let's use times here. And this, again, like in our first calculation with even numbers, becomes a squared to the power of k times a, which is a times a to the power of k times a. Now, this expression is the same type of expression that we have here with our even numbers. So this takes 1 plus k amount of steps. So we know that k is equal to b minus 1 over 2 from this calculation. So this will be b minus 1 over 2. And then we're doing this one extra multiplication, so plus 1. And that again is an improvement from b. We're almost halving the amount of times that we have to multiply. So this is an improvement in both cases. And now, since we have this optimization for both even and odd numbers, well, that's just any integer. So we can apply this even to k now. We can apply this improvement to k. So we can make a times a to the power of k. We can say that's equal to, if k is even, we can put it back into this algorithm. If k is odd, we can put it back into this algorithm. And then we will get an even more improved time that the algorithm takes to complete. So if we just keep recursively doing these calculations until we hit something until we just can't do them anymore, then we will get an improved, optimized version of this algorithm. And this is exponentiation by squaring. And let's try to implement it as pseudocode. So first of all, let's just say we have a function exp exponentiate over a and b, and we'll say that first of all we need to think this is a recursive function and we don't want it to repeat forever, so it has to stop at some point. And where can it stop? Well, the best place for it to stop is something that we don't have to really calculate. And as I said earlier, there are two special cases of exponentiation where we don't really have to calculate anything. A to the power of 1 is just a to the power of 0 is 1. So we can use these so that we don't have to calculate anything, and so that our algorithm actually terminates. So if b equals 0, then return 1. Else if b equals 1, return a. And these are our two special cases. Now, otherwise, we have to use this algorithm, these two algorithms, depending on if it's even or odd. So let's look at else if b is even. We can do return exp. This is our same function, we're calling it recursively. Let's maybe put this in red like the function itself. Exp a times a to the power of b divided by 2. Now, if b is odd, so we can just say else, because every other number that's not even is odd. We can return a times a to the power of b minus 1 over 2, and multiply this by a. And let's end and say end of the function. So this is our algorithm. Now, this will be a recursive algorithm. There might be a way to implement it so that it's not recursive, but I'm not sure about that. So let's look at the time complexity of this algorithm. Now, in the cases of b equals 0 and b equals 1, this is just going to be constant, so we just check if it's 0 or 1, and oh, it is, so we just return this, and so without calculating anything. But we want to look at the worst case of the algorithm. We want to look at if it's even or odd. So here, let's look at first the even case. So the amount of steps that this is going to take will depend on the amount of calls that we're doing to the exp function. So the time complexity of this algorithm is determined by how many times the exp function is recursively called by itself. So if we have a calculation like a to the power of 10, ignoring what the a argument to the function will be, if we call exp, well, this will call exp because it's even and it's not 1 or 0, so this will make something like a times a to the power of 5. So the important thing is that b equals 5, so this is something to the power of 5. And when we call exp again, because now this is not 1 or 0, we will do something to the power of 2 times a, because this is odd, so we're using this function now. So now we see that it's 2, it's even again, so we're doing something to the power of 1, whatever the answer from this was, to the power of 1, and then this is still multiplied by a. Then we see that this is multiplied by, this is exponentiated by 1, so we don't need to call the function anymore, we just get this, whatever this is, and that's times a. So we call the exponentiation function how many times? We call it 1, 2, 3 times, and we also do a multiplication once, but that's not very important. So we have 3 calls of this function, so this is 3 times, and if we have something like a to the power of 24, we will go to something to the power of 12, because the power halves, something to the power of 6, something to the power of 3, and then because this is now going to the odd territory, it's 3 minus 1 divided by 2, which is 1, and then that just ends. So each of these are calls of the exp function, so that's 4 times. And if we look at this for a bunch of different numbers, what we see is that there's a pattern. It's the amount of times that this is called is equal to, so exp calls is equal to log 2 of b. And what is that equal to in terms of n? Well, we discussed before, in the worst case, the amount of digits in b is approximately equal to k to the power of n. So we can say, in the worst case, we have log 2 of k to the power of n, or which is the same as n times log 2 of k, exp equals. So this is the same as the amount of multiplications in the worst case, and therefore the time complexity will be on the order of mn, time complexity of a multiplication, times n times log 2 of k. And because log 2 of k is a constant, we can just ignore it, and therefore the time complexity is on the order of mn times n. And when we compare this to the time complexity of the original algorithm, which is k to the power of n times mn, this is an enormous improvement. We've gone from a we've gone from an exponential factor of mn to a linear factor of mn. So we have gone from this massively fast growing curve to something like this. And that is an insane improvement. That's a very real improvement of time complexity. So that pretty much wraps it up for this video. So I hope this video was useful to you. I hope you learned something, and bye bye.